Good morning. Welcome to class 25. Today we're going to continue talking about optimization and modeling. And to prepare for Wednesday, you can read for review. Wednesday we'll be doing exam review for the exam that opens on Friday. You have a few WebWorks coming due. 17 is due today, 18 is due Wednesday the 9th, and 19 is due Wednesday the 16th. Written 8 is due this Friday, and check-in 6 is due today. Exam 2 is opening this Friday, the 11th, and it is due on Monday, November 14th. I wanted to start today by going over the worksheet that we worked on at the end of last class, rectangular pegs. We want to find the area of the largest rectangle, which can be inscribed inside a region R, where R is defined as being enclosed by the lines x equals 0, y equals 0, and 1/9 x squared minus 2x plus 9. So this is the curve. Below is a diagram for the region R and a sample inscribed rectangle. You may assume that the rectangle will have sides parallel to the axes. Okay, write the area in terms of both the variables x and y. So the area of this rectangle is length times height, or base times height. And based on the coordinates right here being x, y, its base is x and its height is y. Now we want to rewrite the area in terms of only x. So a of x equals, x is fine, but then instead of y, I'm going to use this expression that y is equal to, because that's the formula for the curve. So it's x times 1/9 x squared minus 2x plus 9, and then I'll just distribute the x. 1/9 x cubed minus 2x squared plus 9x. What is the domain of a of x? So I'm looking for an interval a to b that makes sense for x, that can be plugged into the area formula. So let's just draw a picture of what the function looked like that I'm inscribing the rectangle under. It was like this, and x is sort of the base of this rectangle. So x represents the distance from the origin. So the smallest it could be here is 0. And then the biggest it could be, as I move x to the right and still have a rectangle, would be 9, right? So if x is at the origin, I would have a rectangle with a height of 9 but no width, and its area would be 0. And if x is 9, I would have a base of 9 but no height, and the area would also be 0. Okay, so my domain is 0 to 9, and if I start making my table of values, x and a of x, I can put in my endpoints now. They both give me an area of 0. So you can see that graphically, geometrically, that if x were 0, this rectangle would have no width and thus no area. And if x were 9, the rectangle would have no height and thus no area. You can also plug these two x values into the formula for a of x, and they will both give you 0. Now, to this table of values, I need to add some more x values, in specifically critical points. So I find critical points by taking the derivative and setting it equal to 0. So a prime of x is going to be 1/3 x squared minus 4x plus 9. Set that equal to 0. Now, we could use a quadratic formula, or we could try to factor from here. But factoring can be tricky when your coefficient on x squared is not a 1. So I think I will multiply both sides of this equation by 3 just to make my factoring a little easier. Multiply both sides by 3. And I get x squared minus 12x plus 27 is 0. And that factors to x minus 3 times x minus 9. And my critical points I get are 3 and 9. Now 9 is already an endpoint, already in the table. I just need to add 3. And I'm going to calculate the area when x is 3 by plugging 3 into the area formula. Okay, so a of 3 would be 1/9. Actually, I'll do some of this in my head. Okay, 3 cubed is 27, and divided by 9 is 3. 3 squared is 9, times 2 is 18, plus 9 times 3 is 27, and we get 12. So that is my max. And then I should probably just write a sentence stating my final conclusions here. So the dimensions of the rectangle with max area was the question. Find the dimensions of the rectangle with maximum area. I know the maximum area is 12. I know the x coordinate of one dimension of this rectangle is 3, which means the other dimension would have to be 4, because the area of this rectangle is base times height. I know the base is 3. I know the area is 12, so the height would have to be 4. So the dimensions of the rectangle of max area are 3 by 4. Okay, we have a study lounge in the house with some strange dimensions. This is a curved wall, and we want to fit a rectangular carpet, the largest that we can, in this room. So we're going to inscribe this rectangle under this curve, and we're picking a random location to draw this rectangle. So I chose this as a random x. And then this point up here is on the curve, so it's x comma y. So I want to give the area of the rug in terms of both x and y. That would be the base times the height of the rectangle. The distance from the origin to here is x, which means that the base of this rectangle is 2x. So the area is 2x times the height, which is y. To give the area in terms of only one variable, I'm going to use x as my variable. So I have 2x, and then instead of y, I'm going to write the formula for the curve, because y equals 9 minus 1/4 x squared. And then I'll just distribute, and I get 18x minus 1/2 x cubed. To find the domain, I need to think about what my picture looks like. Remember, it's like a parabola-looking thing. And this was -6 and 6 were the x-intercepts for that curve. So x, which was a random distance over from the origin, the smallest it could be would be 0, in which case I just have a single line, a rectangle with a height but no width. And the furthest I can move x over would be 6. In which case I have a rectangle with a base but no height, and the area is also 0. So I'm going to put those two endpoints of my interval into a table of values for area. Both of these endpoints should give me 0. And if you plug them in here, you do get 0. Now I need to add critical points to that table. So I get critical points by taking the derivative, which would be 18 minus 3/2 x squared. And I solve for x, and I set it equal to 0. And in solving for x, I get 18 equals 3/2 x squared. So x squared is 12. X is plus or minus root 12. I'm going to ignore the negative because it is not in my domain. It's not between 0 and 6. So I'm just going to put root 12 in this table. And then I'm going to calculate the area by plugging root 12 into my formula for area. So let's see. I'll do it up here. Area at root 12. That would be 18 root 12 minus 1/2. Root 12 cubed is 12 root 12. So 18 root 12 minus 6 root 12 would be 12 root 12. So 12 root 12 is my max. That's the largest y value. So the dimensions that yield maximum area was the question. So let's write a sentence with our final conclusion. Of the rug of maximum area are, well, max area is 12 root 12 and x is 12, but remember the base of the rectangle was actually 2x because we went to either side of the origin to build this rectangle. So 2 root 12 is my x. And y, or height, is 6. Because what would I multiply 2 root 12 by to get this max area of 12 root 12? 6. You could also plug x equals 2 root 12 into the formula for this curve to get the y value of 6. Okay, for the remainder of today's class, we're going to just work on a couple more optimization problems and modeling problems. The first is called Parks and Optimization. As a park ranger, you know that the price of admission affects the number of people who enter the park each day. Right now, the price is $4 and 200 people visit each day. After some careful study, a consulting firm says that for each 25-cent increase in admission price, 10 fewer people will visit the park. You and your fellow park rangers decide you should maximize your daily revenue for the long-term health of the park. Let X represent the number of times you increase the admission price by 25 cents. Write a function for the number of people who enter the park in terms of X. So N for number of people in terms of X. Okay. So right now, 200 people visit each day, and that's going to decrease, so minus, every time you increase the price. It's going to decrease by 10 people every time you increase the price. So this is a little bit tricky because you might be tempted to do a slope here that's per dollar, right? How many fewer people would attend the park per dollar increase in price? But it's not per dollar, it's just per price increase. okay, of 25 cents. So every time you increase the price, 10 fewer people will come. Okay, using our function from A, write a function for the total revenue of the park. Okay, so our revenue is going to be number of visitors times the price per visitor. That's all the money that comes into the park, revenue. Just take the number of people that come and multiply by how much they pay. So we have a formula for number of visitors. That's what we did in part A. So that was 200 minus 10x. And then the price they pay, well, right now they are paying $4. And X represents the number of 25-cent increases to the price. So we have 4 plus 0.25x. And then if I just multiply those together with a quick distribution, I get 800 plus 10x minus 2.5x squared. To determine what admission price will maximize the daily income of the park, I should think about the domain for price increase. Okay, so the domain would be, the smallest price increase would be 0, right? So we had no 25-cent increases. Although maybe we should consider whether or not we reduce the price, in which case we could go down as far as $0 admission price, which means we could have 16 price decreases of 25 cents. So I could go down 16, I could decrease the price 16 times until I get to 0. I guess I could include the negative 16. Right? And then I could go up to infinity. Could increase this price all the way up to infinity. Okay, so our standard approach here is that we make a little table and we put the endpoints in negative 16, which would give me a revenue of 0, because that would mean that the admission price is $0, which means we get no revenue. We might have a lot of visitors, but they're not paying anything. And then I can't put infinity in here because infinity is not really a number, but I can think about what happens to revenue as x approaches infinity. So I could say the limit as x approaches infinity of my revenue. Okay. This is a quadratic that opens down, so the end behavior is down. So as x goes to infinity, r of x will go to negative infinity. So revenue could really tank as I increase the price. So I'll put this in quotes here: infinity, negative infinity. No, that's not really in the table. It's the end behavior. All right, now to add critical points to the table, I take r prime, which is 10 minus 5x, and I set it to 0. And I solve for x, and I get 2. So I should confirm that this is a maximum, that this will maximize revenue, because I don't have a standard endpoint to check. I don't have a closed interval. I should draw a little number line and confirm that x equals 2 is a maximum. Okay, so if I plug something smaller than 2, anything smaller than 2, into my derivative function, I get a positive number. And if I plug anything bigger than 2 into the derivative function, I get a negative number, which means r goes from increasing to decreasing, which means 2 is in fact a max. So 2 price increases of 25 cents. Yields an entrance price of $4.50 because we started it at $4. We're going to increase it by 25 cents twice. We get $4.50 to maximize revenue. Okay, our next problem is constructing a box out of sheet metal to display widgets in the hardware store. Each box has 2 compartments, here and here, and each holds 72 cubic inches, so that's a volume. And Maria wants to minimize the amount of material, so this is an optimization problem, used to create these boxes. Each box has a base, so this piece of wood or piece of metal on the bottom is the base. 4 sides, 1, 2, 3, 4, and a divider down the middle. There's no lid on the box. Her shelves have a horizontal depth of 12 inches, so that's this dimension that's already labeled, and that is fixed. The other 2 dimensions, this length and this height, can vary. So those are in our control. So let's call this L and H. And write an equation for the total amount of metal used to construct the box. So that would be the surface area of the box. So I'll use A for area. So I have 2 pieces of the box, this front piece and this back piece, that are H by L. So I have 2 LH pieces. Then I have 3 pieces that are this one, and this one that are 12 by H. So I have 3 12H pieces. And then finally I have the bottom of the box, the base, which is L by 12. That's the bottom of the box. Okay, quick simplification would make this 2LH plus 36H plus 12L. Okay, next I'm being asked to write a volume equation in terms of your variables. Well, the volume of my box is L times H times 12. And they told me that each of those 2 compartments holds 72 cubic inches, which means the total volume together would be 144 cubic inches. Which of these 2 equations represents a constraint and which is to be optimized? Well, they asked us to minimize the surface area. That's the amount of material. So this equation is to be minimized. And this other equation that's equal to a number, that's my constraint. Write the equation you need to optimize in terms of only one variable and specify the domain. Okay, well, I'm going to solve this volume equation for L, and I get L equals 12 over H. So now I can plug into my area function 2 times LH, and LH is 12, so 2 times 12, plus 36H plus 12 times L, which is 12 over H. Okay, so area is 24 plus 36H plus 144 H to the negative 1. Thinking about the domain, which they asked me to do here, specify the domain. What H values make sense? So this should be an H. To plug into my area formula? Well, the smallest H could be in the diagram is 0. It's the height of the box. So the smallest it could be is 0, but it can't actually get down to 0 because of the constraint that it must have volume, right? Length times H times 12 must be 144. I can't actually make H 0 because that would give me 0 volume. But I could make H very, very, very small and just compensate by making L very, very, very large. Okay. Which means that I could do the reverse, and the upper bound for H would be very, very, very large, and that happens when L is very, very, very close to 0. So if L were very close to 0, we'd have to compensate by making H extremely large in order to maintain this volume of 144. So 0 to infinity. Find the box dimensions which allow Maria to use the minimum amount of sheet material. All right, so I need to find a critical points. I'm going to take A prime, which would be 36 minus 144 H to the negative 2. Set that equal to 0. I get 36 equals 144 over H squared. So H squared comes out to 4, and H is plus or minus 2. I'm going to ignore H is negative 2 because that's not in the domain for the height. Height has to go from 0 to infinity. And then I'm going to verify that H equals 2 is a minimum, that it will actually minimize the surface area. So A prime, which is 36 minus 144 over H squared, put 2 here. If you put something smaller than 2 into this formula, something between 0 and 2, because the end point is 0, like maybe a 1, you get a negative. If you plug something bigger than 2 in, like 10 or something, 10 squared is 100, 144 over 100 is 1.44, 36 minus that is still a positive number. Okay, so that means that surface area goes from decreasing to increasing, giving me a min at 2. Considering that 2 is my only critical point in the domain, that means that A is always decreasing from 0 to 2. So it's always coming down. And then after 2, it's always increasing. So this is the only possible global min. If there were another min, there'd have to be another critical point. So this is the only possibility for the global min. All right, so I'm just going to write down my final conclusion. The dimensions of the box with minimum surface area are H equals 2, that's what we just figured out, and these were all in inches. Okay, the length L, remember we solved for L at one point and it was 12 over H. 12 over 2 is 6 inches. And the depth was constant. 12 inches.